This is part 7 of the chemical changes topic on AQA GCSE chemistry. It's a dual and triple award topic. I'm going to recommend you pause and have a go at the activities as you go through. In this one, we are going to take a look at neutralisation, and we're going to review the pH scale and pH curves. Now, there is a huge amount of information that you are already familiar with from Key Stage 3. You'll be aware of the use of indicators. You will be aware potentially of the pH scale and examples of acids and alkalis. I'm going to build on that a little bit more. We've got some information that I'm going to talk through over the next minute or two. But I do recommend you pausing and taking the time to read through this carefully for yourself. Now, we can categorise substances as being acidic, alkaline, or neutral. If we talk about an alkali is actually a form of a base. A base is something that can be neutralised by an acid, but an alkali is one that can dissolve in water. Now, in earlier videos, we looked at metal oxides reacting with acids to make a salt and water. Metal oxides are bases. We also looked at metal hydroxides reacting with acids to make a salt and water. Metal hydroxides are soluble in water, and therefore they are alkalis. Now, acids, if we're looking at some of the key conditions here or characteristics, acids have a very sour taste. You'll be familiar from that with ethanoic acid and citric acid, that's vinegar and lemon juice. Actually, all acids have got that very sour taste, but they are incredibly corrosive. Pure water is neutral, so we call something neutral if it is neither acidic or alkaline, and we'll see what that looks like on the pH scale a little later. This equation at the bottom helps to show what happens when hydrogen chloride gas is put into water. It breaks down and it ionises into H+ ions and C- ions, and you'll notice that they are now aqueous. Moving on, some key information here. It's actually the H+ ion that we saw in that equation that makes hydrochloric acid acidic. All acids release H+ ions when dissolved in water. If we take a look at alkalis, at the other end of the scale, we've got an alkali here, sodium hydroxide, which is solid. It breaks down into Na+ and OH- ions. And in this case, it's the OH- ions that determine the characteristic of it. OH- ions are formed when alkalines are added to water. Now, we can measure whether something is acidic or alkaline, or indeed if it's neutral, and we do that using indicators. And with indicators, you might have things like litmus, which will simply tell you whether something is an acid or an alkali. But you might use an indicator that tells you how strong the acid or alkali is. The pH scale runs from pH 0 through to pH 14. pH 7, there in the centre, would be a neutral solution. The further away you go from 7, below 7, it becomes more acidic, and above 7, it becomes more alkaline. And final bit of information here, we could measure that in two different ways. We could use universal indicator, which will go different colours depending on the pH that we're measuring, or we could do the measurements digitally using a pH meter. So a lot of information there. Have a go at the questions that follow and see how you do. So an alkali is a type of base, but what special property does it have to make it an alkali? Well, as we've already discussed earlier in the video, it's a base that will dissolve in water. What examples of acids were named and what flavour did they have? There were two that were mentioned within the information provided. That was citric acid, which you find in citrus fruits like lemons, and ethanoic acid, which is the chemical name for vinegar. And if you think about the flavours of both of those, they are sour. A couple more questions for you to try here. So hydrochloric acid would be sour, but we wouldn't taste it. That's because it would be too dangerous. It's a strong acid. It's incredibly corrosive. So you would be putting yourself at risk. 4 and 5 are incredibly important pieces of information to remember. An ion responsible for making acids acidic, that's H plus ions. And the ion responsible for alkalines being alkaline, that's if there is the presence of OH minus ions in solution. And we also saw in the previous video what happens when we neutralise. So when we were doing salt preps, we did neutralisation ionic equations. So have a go at these questions. And those two ions, if I take an H plus ion and an OH minus ion, then I put them together, I'm going to make H2O. And that H2O is not aqueous, it's going to be a liquid. And what would happen if we put nitric acid into water? Now, earlier with HCl, we did that as gaseous. I'm actually going to show this one as aqueous HNO3, as in slightly aqueous, but I'm going to dilute it down. And it dissociates into the two ions, H plus and NO3 minus. And remember, it's the presence of H plus ions that makes HNO3 acidic. Some more questions for you to try. So for number 8, an equation to show what happens when potassium hydroxide dissociates. Now, metal hydroxides are generally solid, but we can break them down into the K plus and the OH minus ions. And it's the OH minus ions present that make potassium hydroxide alkaline. What colours would we see with litmus paper if it was added to an acid or an alkali? Well, for an acid, we get a red colour. We have to remember that. We have to remember an alkali would be blue. And it does make sense that if we have a neutral solution, we would expect our litmus paper to be a combination of these two colours, therefore purple. But the litmus scale or the litmus paper tells us whether something is acidic or alkali. What's the advantage of the pH scale? Well, what that does is tell us how strong an acid or an alkali is. The litmus will only tell us if it's acidic, alkali or neutral. And we need to consider a little more about that pH scale. Have a think about this question. So I've got 4 potential answers here: strong acid, weak acid, strong alkali, or weak alkali for something with a pH of 6. Well, let's start by drawing the pH scale out. It does go down to 0. Commonly, you won't see it go below 1 at GCSE, but it runs from 1 through to 14, where we have neutral at 7 in the centre. We have a strong acid down at pH 1 and a strong base or a strong alkali up at pH 14. So if I consider pH 6, which is not much below 7, it's below 7, so that makes it acidic. It's on the acid side of the scale. But because it's very close to 7, it's certainly not going to be a strong acid, so it's going to be a weak acid. We're going to move on to look at pH curves, and this is a practical that you will probably have done within lessons. You can do it using burettes that you'll have seen in titrations. In terms of the method, you will take a sample of acid or alkali and you will neutralise it slowly by adding small portions of alkali or acid to it, and you will measure the pH after each addition. Now, in terms of the questions, we're going to discuss pH curves in a moment's time. If you have got in any of your notes from any of your lessons data that you have collected, this is a good opportunity to practice graph plotting for you. But let's look at these questions below that again help to reinforce some of the key points that you are going to have to remember. Acids will produce H plus ions in aqueous solution, whereas aqueous solutions of alkali contain OH minus ions. But if a solution has a pH of 7, we would say it's not acidic, it's not alkali, we say that it's neutral. pH of below 7, that would be an acid, and if the pH is above 7, it's an alkali. I cannot reinforce how important it is to get these key terms correct and confidently understood and remembered. How can we measure pH? Well, this was discussed in the earlier part of the video. There are two ways really. One, we can use a universal indicator. That might be paper, it might be solution, and you will get a reference card to allow you to check the colour to find the pH. But far more effective is the use of a pH probe. That will measure pH digitally. You can do it to a higher level of precision. You can be a lot more confident within your results. The ionic equation for every neutralisation reaction is the same, and we've seen this in this video already and in previous videos. What is that equation? Well, I'm actually going to do it twice to prove that it's the same for each neutralisation reaction. Let's start with the reaction between nitric acid and sodium hydroxide. Now, for an ionic equation, you break down anything that's ionic and that's aqueous. That's everything in this equation, apart from water, which is a covalent molecule. So my HNO3 breaks down into H plus and NO3 minus, my sodium hydroxide into Na plus and OH minus, my sodium nitrate into Na plus and NO3 minus, and then my H2O. I'm then able to remove my spectators, the things that appear on both sides of the equation unchanged. Na plus, gone. NO3 minus, gone. And that leaves me with H plus OH minus goes to H2O. Let's go on and do this with a different acid and alkali combination. I've got H2SO4 and KOH, sulfuric acid and potassium hydroxide, making potassium sulfate and water. Again, water is covalent, but we break all of the others down to their ions. Got to balance it first, obviously, but then we break it down. The sulfuric acid, 2H plus and SO4 minus, 2KOH, 2K plus and 2OH minus, K2SO4, 2K plus and SO4 minus, and I keep my H2O the same. Now let's get rid of the spectators. SO4 minus is on both sides, let's remove. 2K plus is on both sides, let's remove. And you can see that what we're left with is balanced differently, but it's exactly the same neutralisation equation that we saw above. So now let's move on and look at those pH scales. This is a really important shape to learn. You will need to remember it. We can see here that we started with an acid and we've added an alkali. We know that because the pH has started below 7 and ended above 7. Have a go at the questions below. So the initial pH of the acid is 1.6. We can see that from the reading that we have here. Use the graph to estimate the pH when 10 cm cubed of alkali has been added. Well, I'm going to draw my line up and across. It's gone to a pH of 2. I've added quite a lot of acid there and the pH has barely changed. You get a very slow change, rapid movement around the point of neutralisation, and then the rate of pH change slows again. And that will always be the case. And then finally, what would it be at 18 cm cubed? Again, let's draw that line on, draw that across, and we get to 11.8. Again, just to remind you, you must familiarise yourself with the characteristic shape of this graph. You may need to plot it, you may need to draw a line of best fit, you may need to read and analyse data from it. Let's have a think about what else we can see from here. Let's mark on the graph where the acid is in excess, where the alkali is in excess, and where the neutral point is. Well, the acid is going to be in excess up until we reach pH of 7, which is here. So it's until we get to this point. We are then neutral. Our alkali is in excess after the point that we're neutral. And we're really looking at a couple of drops from going from acid in excess to alkali in excess. A very small volume change gives a very rapid change of pH. But this area is the neutral point. What volume of alkali was needed to neutralise the acid? Well, you read across the graph, you look at where pH was 7, it's here, you read down, and the volume is 15 centimetre cubed. That takes us to the end of this video. Thank you for listening, and goodbye.